Hello everyone, welcome. This is class ECE317 digital signal processing. Last time we have introduced a method to calculate the convolution of two signals by Fourier transform, DTFT, discrete time Fourier transform. The convolution of two signals, if we apply the Fourier transform on it, we can have a multiplication in the frequency domain. So the multiplication will be simpler than the convolution, right? So we can use a multiplication to replace the convolution. Of course, we need some other works. We need to perform the Fourier transform before we times them together, and after we perform the multiplication, we also need the inverse Laplace Fourier transform. So this is a kind of a shortcut. Is an easier way than do the convolution directly. Not always, but in most cases, this method can make the calculation more simpler. Okay, today let's study more about these kind of things. These are ECE317. Right. This is the this is fourth week. Right. Fourth week, Monday. We consider the convolution of two signals. We perform Fourier transform, discrete time Fourier transform, DTFT. Then we can have it is a multiplication of capital X and capital Y. These capital X and capital Y, they are the Fourier transform of the signal X, lowercase x and lowercase y. Right? We have this one, and then we perform the inverse DTFT. We have this that equal to something, right? Equal to something. So this is the method. We do not perform the convolution directly. We go by this way. Yeah. Okay. Then we can apply these two systems, right? We know a system, the output is a convolution of input with the impulse response, right? X of n. This is the LTI system, and we can just put h here because h of n actually give us all the information about the input output of the system, right? If you know what is h of n, then you can find any output where input is given, right? This is a input convolution with the impulse response, right? H is the impulse response. Okay, now we use a Fourier transform. The thing can be work like this. X, this one, by Fourier transform, the DTFT, we have X, okay, capital X. Then this H, we have capital H. Okay, then these two, we do a multiplication, we have Y. We have Y. Times these two together, we have the Y. Y is now is XH. Here is XH, right? X times H, we get a Y. And then we perform the DTFT, the inverse of DTFT, then we can have Y of n. So we can work like this. Alright. And by this way, of course you need to do Fourier transform. You avoid to do the convolution. You replaced by multiplication, and also you need several transform, right? DTFT, DTFT, and DTFT the inverse. Right? You need these three transform, two forward transform and one inverse transform. But this one, you can think if you change the input, then you need to change this capital X, but H is the same, right? H is the same. No matter what is the input, you can always use this H. So you can think this H, you already have it. You don't need to do it anymore. Just one time. Like even you want to calculate 1,000 times for 1,000 different input, H is still this H, right? So you only need this one and this one. Suppose H is given, right? In calculation. So DTFT from input to the frequency domain of the input. Then times this H, you have Y in the frequency domain. Then go back, you have the final answer. What is output? Yeah. And this H, we have a name. H e to the j omega is called the frequency response. Frequency response. Frequency response. The meaning is the impulse response. It is the impulse response. Response, but in the frequency domain. Right? It's a transform of the impulse response. So it's the impulse response in frequency domain. We call it the frequency response. Frequency response. Then how to get this capital H? By definition, this is how to find H. It is a DTFT of H of n. This is one method, basically. It's a kind of definition. But we have another way. We have another way to find this one. This is the first way. And second way, if we know the difference equation of the system, we can find H from the equation. Yeah, this is a good feature, you know. If you use this way, this is basically the definition way. You need to find the impulse response firstly. Right? You start from the difference equation. You use third of n, the impulse, unit impulse as the input. Then you try to solve the equations. You can get the impulse response. We have some examples like that, right? And then after you get impulse response, you perform Fourier transform to get capital H. So you need 2 steps, and each step may cause some works, maybe a lot of works. But now we can use we can find it directly from the equation. Yeah, that will be simple one. We use an example to explain it. We consider the system y of n minus 1/2 y of n minus 1 equal to x of n. Okay, we consider this one. Then, yeah, you can solve it, right? If x is a third of n, You plug in what is dirt of n, then you can have it. You can do it. This one is not so complex. I put n, this is -2, -1, 0, 1, 2, 3, 4, for example. Then the x, which is dirt now, right? It's dirt. Then should be 0, 0, 1, 0, 0, 0, 0, right? The impulse, only one value at 1. All the others are 0. Then what is y? What is y? Okay, y you need to write this way. Y is x plus previous y. Previous y. But what is the previous y? You can think in the beginning, the system has nothing. So for negative n, for large negative n, the y of n is just 0. So y of n will be half of 0 plus x. And for negative n, x is 0. So you have h of n. Now is y of n, right? The output, it is 0. Half of 0 plus 0, right? Half of 0 plus 0. And this value is also half of this and this one. You do summation, you get 0. Okay, you have same thing. Times half, and this one you do summation. You have half, do summation, you have 1/2. And this is also half, then 1/4, right? And half of this, do summation, you have 1/8. Keep doing like this way. 1/16. And more, right? Every time is 1 of 2 to the n, things like this. If here's the n. Say this n. And for negative n, they are 0. So we have h of n is 1 over 2 to the n times u of n, right? So we have this one as the answer, with the answer. Alright, now we try to use Fourier transform. Fourier transform. Say this is 1. We perform method 1. Then the method 2. We perform DTFT, discrete time Fourier transform, on both sides of 1. Now, then what will be the result? Okay, y, there will be y e to the e to the j omega, right? This is y. And minus half of, okay, we have a shift. Here's a shift of y. Then what will be the result? Last time I suggest you go over the tables, right? Table of the Fourier transform. Anyone did it? The tables. All right, you get it? You see the second one. Second one. Make it large. You see the second one. X of n minus some nd is a shifted signal of x. Then its Fourier transform as capital X times exponential power e to the negative j omega nd. So here is a negative nd here, right? Negative nd here. Then here you have a negative nd times this j omega. Alright, so let's go back to our topic here. Right. So this one, y n minus, this is nd. This is shifted by 1. And here's e to the j omega times negative 1. Right, so it's negative j omega. Alright. And the other side is a capital X of e to the j omega. But we know x is dirt, right? Unit impulse. So we know capital X is what? Is 1. It's just 1. Yeah, you check the table, another table. We have 3 tables for DTFT, right? Another table, you can find this one. This is 1. So this is 1. Okay, then we can have capital Y equal to 1 over 1 minus 1/2 e to the negative j omega, right? And this is h of e to the j omega, the frequency response, right? Yeah, because input is dirt. Input is dirt, then output will be the h output. So this output now, this output is that h. So we have h. We have h. And then this one, we do the inverse dTft. It will be 1/2 to the n times u of n. Yeah, this one is also in the table. This is we need another table. A third table, 3 tables. Oh, yeah, here. You see, the fourth one, a to the n times u of n. This side is 1/1 minus a to the e to the negative j omega. In our example here, we go back, right? We'll go back. So this is the impulse response. So we have the impulse response. We have impulse response. We also have this y, this h, the frequency response. We have this, and by the first method, we can also here the dTft. We have capital H e to the j omega. You also use the table. This is 1/1 minus 1/2 e to the negative j omega. You get same thing. But this method is quite simple. Why it is quite simple? You look at it here. The equation, the x side, this is the side of the input x. You only have one term with coefficient 1. So here you see the numerator is 1, according to the x side, right? The side with x, right? This is 1, just 1. And the other side, the signals are the output and it's shifted, right? Shifted output and output. And coefficient, I have 1 and 1/2. So here are negative 1/2. So here's 1 and negative 1/2. The first term without the shift, so here's just 1. Second term shifted by 1. Then you have e to the negative j omega, right? We know shifted means you times this term in frequency domain, right? Shifted in time domain, then in frequency domain you times these this power, right? Yeah. Okay. Then we can have one more complex thing. Example. I have system with differential equation like y to the n plus 1/2 y to the n minus 1 minus 1/3 y of n minus 2 and plus 1/7 y to the n minus 3 equal to x of n plus 3 of x of n minus 2. Now what is the frequency response? Find the frequency response. H of e to the j omega. Alright, what it is? Okay, you can imagine if you want to plug in the value of impulse here in the input side, and it will be hard to solve what is output, right? The equation is complex. But now I can write this directly. Right? Yeah, you find the h of n, then perform inverse dTft to get this one. You need a lot of work, and even very hard. And now I can have this directly. What it is? It is a fraction. The numerator part of this fraction is coming from this input side. So input side, you look at here. We have two terms. The first one is x itself, just x, nothing change, so it is 1. Second term, we have a coefficient 3, so plus 3. And we have a shift on the time, right? X is shifted by 2, minus 2 here. So this is E minus 2 times j omega. Alright, this is numerator. So I just write it directly. And the denominator is the same way. You look at all these terms with output. The first one is y, just y, so nothing changed. And the second term, you have coefficient 1/2 and shifted by 1, so e to the j omega times -1. And then third term, I have -1/3 as a coefficient and shifted by 2, so negative j omega times -2. And the last term is 1/7 times e to the negative j omega, now is 3, right? Shifted by -3. Okay, this is the frequency response. So you can write this directly. And you can do the inverse way. If you know the if you know the frequency response, you can go back to the equation, right? Directly. You just numerator according to the input and the denominator according to the output. That's it. Alright, we can check another example. We consider moving average. Average. Moving average system. We can have more terms, like 10 terms. Alright, it's 1/10, the x of n plus x of n minus 1 plus until x of n minus 9, right? 10 terms. Alright, this is moving average system, 10 terms. Then what is the frequency response? So we can have h of e to the j omega. I can write it directly. Numerator, I have 1/10. The first term just 1/10. Second term is 1/10, right? Coefficient still at 1/10, and e to the negative j omega. And okay, all of these coefficient are same, 1/10, and shifted. Now they shifted by 9, -9, j omega times -9. And the denominator, oh, it is just 1. So actually this is just the numerator part. You don't need the denominator, right? Just numerator part. And actually here you see, this is a, we can do some change, right? This is a kind of it is 1 plus, you see, it's a geometry series, right? Summation of some e to the negative j omega plus e to the negative j omega square of it, e to the negative j omega cube of it, until e to the negative j omega to the 9th. So we have this one, 1 plus a square plus dot 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 until a to the 9th. What is this? Now we have formula. Do you remember that? It is 1 minus a in the denominator, and numerator is 1 minus a to the 10th. We have this. We have this. This is a formula. This is a formula. And if you do not sure what it is or how get it, you can just try this. 1 minus a times 1 plus a square plus a 9th equal to what? 1 times all of these, right? And a times minus a times all of these. So minus a times, first one is a times 1, then a times a is a squared, a times 8 I get 9, and a times a to the 9th I get 10. Okay, the first summation subtract second summation, what will be the result? Oh, a cancel, a square cancel, all of them cancel, only equal to only the first term and last term left, right? Okay. We have these. So you see, This one equal to this one. Then you divided 1 minus a to that side, you get this one. Alright. Okay, so this equation I can write as 1 over 10 times 1 minus a. A is now is e to the negative j omega, right? This capital A now is this one. And the numerator is 1 minus e to the negative j omega times 10. So we can have capital H is this one. And now we can go back. We can go back to the equation. If we go back from here, we can have the original equation, right? But we can also go back from here, from frequency domain to the time domain. What will be a difference equation for this system? It looks like this, right? So you know this will be 1 over 10. Which side you want to put? You put this as a denominator, right? 1 over 10. So this is a 10. This is a y side, right? This is y of n. 1 is just y of n. And this is a minus y of n shifted by 1. Right? You have this one. And x side, it is 1, that is x of n. And minus x shifted by 10. Oh, we have equation looks like this. You see? Different, right? These two are different. We have two different equations, but they are for the same system, because you go to the frequency response, they have same frequency response. Then if you want to go to the impulse response, they will have same impulse response. Alright. Yeah. Okay, this is one example. Now let's let me see. Yeah, let's do this kind of things in computer. We can have more visible, more visions, right? You can look at it. We can have some graph things. Go to MATLAB. Okay, we start like a file here. New M file. M file is a file for the MATLAB. You can put the code, all the code together in this file and run it, right? Run the whole file. Here I want. Okay, I just use this one as an example. Right? I just use this one. We have it, already have it, right? We use this one. The moving average. We use this moving average as an example. Moving average. Then we want to see what is capital H. We have two formulas, right? We have two formulas. We can use either one to find the frequency response. Then I give you both. I have coefficient for, we have this one, right? Field of the numerator part is 1/10. 1 over 10 is 0.1, right? 0.1 times I need a 10 of 1, so I times this. I times ones. This is a function in the MATLAB. 10 of 1s. So ones give us a matrix. Ones give us a matrix. We can have a look at here. You can try ones. Not here. Ones. Right. Ones of like 2 and 4. This will give us a matrix with size 2 and 4. 2 rows, 4 columns, and all the elements are 1. You see? Yeah, this is 1. Alright. So now I want 1 row and 10 columns. So I need this 1 row and 10 columns. So this gives us 1, 1, 1, 1, 10 ones. And times 0.1. So actually this is just a 0.1, 0.1, 0.1. Okay. Yeah. 0.1, 0.1, 0.1. Yeah. It is just this one. You can run this. We can run this to see what it is. Yeah, the system will give you the frequency response. We can also give a graph of it. Now I give a graph of it. The first one. Okay, figure 1. This is first graph. I need to plot this one. I need a W. Okay, at both cases we need W. So I use W equal to. I start from like a negative pi. I give more. And negative 2 pi to positive. I use that point 1. Okay. That's too small. Maybe slow. I use 0.4. Okay, that should be enough. Until negative 2 pi to positive like 4 pi. All right, 4 times pi. Okay, I have W, and I want this one. So I have 10 terms. If I write all of them together, there will be a lot. I use a loop, right? I use a for loop. For I run from 0 to 9. Then I have that capital H. I say capital H1 equal to. I need 1/10. That will be H. 1/10. There will be. Okay, I use a notation for this. I have A equal to. I put this A equal to this one. 0.1 times 0.50. This is A. I have 10 of 0.1. The filter is the input side is this and output side is 1. Oh, I missed this one here. So this side is just A. I don't need to calculate again. Right? This is A. A is the coefficient for the input, and the output side is just a 1. And the W is the frequency I want to use. Then for figure 1, I need to plot H1, capital H1, which is a H1 plus a new term. The new term will be A of I, right? A of I times exponential power of negative j times omega. Am I good? Oh, this I run from 0 to 9. No, I need I will run from 1 to 9. I use n. Okay, this is n. N equal to 0 to 9. Then this will be AI, but you know, MATLAB, all the vectors start from the index start from 1. So here should be n plus 1. Then e to the j omega times n. Okay, this is one term, right? The one term, and n run from 1 to 9, 0 to 9. N run from 0 to 9. That is n. Okay, so I have this one. I have H1 and the n. Okay, then plot H1. H1 use W as a x-axis and whatever 2 or W and H1. I run this one, and is it good? Oh, I need H1 firstly. So H1 in the beginning, H1 is 0. H1 is 0. So just W times 0. Right. So yeah, I needed H1 has the same size with W. So I use W. W times 0. Its value is 0, and the size is as same as W. So H1 is this one. In the beginning, this is 0. Then when I run this loop, for every n, I add one more term to H1. So when I finish these, I contain all these terms. Then there will be H1. Okay, let me run it. 1, 2, 3, 4, 5. working? Yeah, it's wrong. Oh, I need to give a place. I say this is a. I need to save it. I have ECE317. I have a folder with codes. My lab code. I already have lecture 2. This is lecture which one? Lecture 4th Monday, right? Lecture 4th Monday. See. I add this direction to my lab path. Okay, we have this one. It looks like this. Alright. Because I use from negative 2 pi to positive 4 pi, right? 3 pi, 4 pi, 4 pi. Negative 2 pi to positive 4 pi. Positive 4 pi. So it looks like this. And remember, for the integration, to go back from the frequency domain to the time domain, the inverse dTft. Yeah? It is an integration just one period, right? This one. Remember this. So x of n will be 1 over 2 pi. The integration here is one period. You can use any, like a negative pi to pi or 0 to 2 pi. Then here's a capital X e to the j omega times e to the j omega n d omega, right? We have this. So when you calculate, go back from frequency domain to the time domain, the inverse of dTft, the integration only need one period, one cycle. So here in the graph, you can use any from 0 to 2 pi or from anywhere. You just with interval length 2 pi. They all be same because this one is a period. This one is periodic. This is capital H. This is capital H. Okay, we can also see use the second one, right? We have two formulas. I just have this one. I can also give it by this way. I have this one, right? So by this one, I use H2, which is okay. This is just one formula, so it is 1 over 10 times. Okay, yeah, I can write 1 minus exponential power of negative j times omega times 10. This is a numerator, and divided by denominator is 1 minus e to the exp to the negative j times omega. Am I good? Oh, here divided. You need to put dot here because both numerator and the denominator, they are vectors. They are not single value, right? Because w is a list of value. W are the values from negative 2 pi to positive 4 pi with step point 4. So we have a lot of values, right? In W. W is a list of value. So the exponential power is also a list of value. So both numerator and denominator, they are vectors, not single value. So when you divide it, you put a dot. Put dot, that means the division now is element by element, right? The first element of the numerator divided by the first element of the first element of the numerator divided by the second number, the first number of the denominator. I'm sorry, I confused myself. Yeah, so it's like element by element. This is H2, and then I plot it. Okay, this one is figure 1. First plot is figure 1, and second plot is figure 2, and the plot still use W as a x-axis, but now it's H2. Alright. Oh, this one is okay, it's just a case. I can use a plot. in generally this one is a it is a complex number. So let me see. So this one should be still real result. Okay, we're lucky here. In this example, in both way you calculate this capital H. This one is the result is real. That means no imaginary part. No imaginary part. Actually, they are complex numbers. Right? You have J here, but in some cases they are not. They do not have the imaginary part. No term in J part. So I have this result. Actually, they are same, right? They are same. Yeah, just a different scale, right? This is small graph. That's a large graph. The same thing. And we have same thing. So you can use either way to calculate it. And here we have another method. Method is we can find this one from the. Okay, I need an impulse response. So we can find the frequency response by DTFT from the impulse response, right? So what is the impulse response right now? Do I have time? I have 6 more minutes. Okay, I can have it. Now, h of e to the j omega equal to 110 plus 110 e to the negative j omega plus 110 e to the negative j omega 9. Then we perform DTFT inverse DTFT, the inverse way. We will have h of n, right? Then 110s go this side will be what? This one. Do I have this in my table? Yeah, you see? In frequency domain is 1, then go back is dirt. And the second, if in frequency domain is exponential power, then in the time domain is a shifted dirt, right? Shifted dirt. Okay, so let's go back to our problem here. This one is 1 over 10, and this go back will be shifted dirt, shifted by 1. And okay, last one is the same dirt, shifted by 9. This is h of n. And you can use a graph to see you have 1 dirt times 1 over 10, right? And shifted dirt, shifted by 1, shifted by 2, until shifted by 9. This is a h of n. It is this one. You can also list the value h of n equal to 110, 110 until 110. This is a n equal to 0. This is a n equal to 9. And the normal numbers. You can just write in this way. You do not need to put dot dot dot. You write in this way means all the other values they are 0. Alright. If like this, here's n equal to 0, then you have this dot dot dot. That means unknown. You don't know what are they. Or some formula, if you have a formula, looks some regular, or some formulas. Some formulas. Yeah, the things like that. Right. And you write in this way, no, you do not have those dot dot dot, then okay, all the rest are zeros. So this is h of n. This is h of n. And we can find the frequency response start from this h, right? We perform DTFT, we can have h of e to the j omega. And this one we can also work by computer. However, the result of the computer is a kind of a discrete result. Right? We can have a look here. We can have a look. Now I want to find h. H is what? H is H is 110 times or it's just A, right? Same with A. You get it? You can find it. A is 10 of 1/10, right? 0.1. I have 10 of 0.1, and this impulse. Now this impulse frequency, impulse response also I have 10 of 0.1s. So H is just A. H just A. Okay, H is just A. Then we perform. I want another H3. H3 is FFT of A. I perform this. FFT. FFT. This is a fast Fourier transform function in MATLAB. This is MATLAB function, building function. You can use these to calculate the Fourier transform of a sequence of numbers. But actually this one is a DFT. Remember the first time I introduced the method how to represent these in terms of summation of some functions, right? We want to find formula of it, and how to calculate those coefficients, right? That is FFT. And now I have H3. I can also plot it. I can plot this H3, but the exercise will be it will run from 0 to 2 pi. So the exercise will be 0 to 2 pi, totally 10 values. So 0 to 9 times pi times 2 pi times 2 times pi. Oh, this one should be here. Oh, this is 0. Sorry. 0 should be, I need a shift. 0 to 9 times 2 times pi. I plot this. This is a figure 3. I have 3 figures. Okay. Let me run it. If you want to run, you can. This is debug here. You put this one, save and run, right? Save and run. Oh, I got something mistake. This is a arrow here. Which line? In the line 23, column 16, right? Line 23, column 16. Oh, this one. Simulcast. It should be just this one. All right. Okay. We have this one. Looks like this. So are they same? Now I can put them together. You see, I can put them together. When I figure 2, I have this one, right? I have this one. So I can no, I have figure 1, right? So I can hold figure 1. Oh no, hold figure 2. Hold figure 1. That doesn't matter. Hold figure 2. Hold on. So now figure 2, I read these. I don't use these. Now the second and the third plot will be same with second, and here I use each point I use a circle here. I use circle. You will plot as a circles. All right. Oh no, why it's not? I put it wrong X, right? Let me see. I want to put this together. Which part I getting wrong? This is a W from, this was W from negative 2 pi to positive pi, and here's I have 9s. Oh, I need divide by, sorry, it's 2 pi over n, right? Divide by n. 2 pi over n. Remember last time we did that? Yeah, divide by n. This time it should be good. Okay, Now it's here. You see the point down here. So by the FFT function, we have some examples from the whole frequency response, right? The curve, this curve is the frequency response, and these circles result from the function FFT. You get it? FFT. So I will say you can also calculate by FFT, give some symbols of h of e to the j omega. So this is h. FFT of h gives some symbols h of n, give some symbols of capital H of e to the j omega. These symbols, the symbols according to the frequency equal to from 0 to 2 pi, with step is 2 pi over n, and do not contain 2 pi. Contain 0 but do not contain 2 pi. Totally n symbols. Like this way. Yeah, I use the notation of the MATLAB notation, right? Okay. All right. That's all for today. See you next time.